final volume? And that's the answer of this question. Now we shall discuss a very important article, that is thermodynamic definition of ideal gas. Since for an ideal gas we can write energy as a function of volume and temperature, therefore dE can be written as dE by dV at T dV plus dE by dt at V dt. But dE by dt at V is equal to Cv, therefore dE will be equal to dE by dV at T dV plus Cv dt. Now consider first law of thermodynamics, according to which dQ is equal to dE minus dW. Therefore we can write dQ is equal to dE by dV at T dV plus Cv dt minus dW. Further, consider expansion of ideal gas into vacuum, that is free expansion at constant temperature. Therefore, dW is equal to 0, dQ will also be equal to 0, and dt is also equal to 0. Hence, dE by dV at T dV is equal to 0. But dV cannot be 0 as the gas is undergoing expansion. Therefore, we conclude that dE by dV at T is equal to 0. Hence, internal energy of an ideal gas is independent of its volume at constant temperature. This becomes a thermodynamic definition of ideal gas. Let us also learn derivation of T2 equal to T1 into V1 by V2 to the power gamma minus 1. Consider the expansion of 1 mole of an ideal gas under adiabatic conditions. Hence dQ is equal to 0 and dW equal to minus PdV. dE is equal to Cv dt as we know. Therefore, using first law, that is dE equal to dQ minus dW, we have Cv dt equal to minus PdV, and that's further equal to minus RT upon V dV. Or we can write Cv upon R dt equal to minus dV by V, or this can be written as Cv upon R ln T equal to minus d ln V. Integrating it, we have integration T1 to T2 Cv by R ln T equal to integration V1 to V2 minus d ln V. This becomes ln T2 by T1 raised to power Cv by R equal to ln V1 upon V2. Or we can write T2 by T1 whole raised to power Cv by R equal to V1 upon V2. And therefore T2 becomes equal to T1 into V1 upon V2 raised to power R upon Cv. Now using Cp minus Cv equal to R and Cp by Cv equal to gamma, we can write T2 equal to T1 into V1 upon V2 raised to power Cp minus Cv upon Cv. That can be finally written as T2 equal to T1 into V1 upon V2 raised to power gamma minus 1. Now we come to part 3 of this chapter of thermodynamics, where we have to study second law of thermodynamics. Before we start discussing second law of thermodynamics, it is necessary to understand an important drawback of first law of thermodynamics. So, let us have limitation of first law. We have already seen many examples of natural or irreversible or spontaneous processes. Let us consider one of them, say flow of heat from a hot body to a cold body when brought in contact. It is a matter of common experience that heat will continue flowing from hot body to cold till both bodies attain the same temperature. Due to this flow, internal energy of hot body has decreased, and exactly by the same amount it has increased for the cold body. Thus energy has been conserved. In other words, the law of conservation of energy or first law of thermodynamics is justified or has not been violated. Now suppose, for the time being, if this spontaneous process, that is flow of heat, would have gone in the opposite direction, that is, from cold to hot body, would it be a violation of first law? The answer is no, because in that circumstances too, the total energy of the universe will remain the same.